today we're going to talk about 13.3 and 13.4, looking at other ways to express equilibrium and different types of equilibrium. So we're going to look at pressure first. So we can also describe equilibrium in terms of pressure. So if you take a look at this equation, this is modified from the ideal gas law. You can see that one of the differences is this capital C value, which is equal to N over V. And so capital C represents a molar concentration of a gas. And so we can use an example to explain this. Let's look at the synthesis of ammonia. And so here's our equilibrium expression. We've got the product squared because of the 2 right here, N2 times H2 cubed. We can also write this in terms of the molar concentration, same idea. And then if we want to do this in terms of partial pressure, we can write the same type of reaction, or same type of equilibrium expression, except now we're using partial pressures instead of concentrations. So let's look at an example. It says the reaction for the formation of nitrosyl chloride is 2NO as a gas plus CO2 as a gas goes to 2NOCl as a gas and was studied at 25 Celsius. Pressures at equilibrium were found to be pressure of NOCl, pressure of NO, and pressure of Cl2. And they want to calculate the value of K sub P. Okay, so we know that K sub P is equal to the partial pressure of the reactants, partial pressure of the products divided by the reactants. So our only product is NOCl, and because there's a 2 in front, we're going to square that value divided by the partial pressure of the reactants. So we have partial pressure of NO squared times the partial pressure of Cl2, and that doesn't get a superscript or a power because there's a 1 when it's balanced. So now let's plug in some values. So, and just also to point out, these are pressures at equilibrium, just like we use concentrations at equilibrium. So we have 1.2 atmospheres on top, and we're going to square that. Divided by, for NO, it's 5 times 10 to the negative 2 squared times 3 times 10 to the negative 1, and that's just to the first power. And I don't have my fancy calculator anymore, but if we plug everything in, you should get 1,920. Remember, K sub P, just like K, has no units. We do need significant figures, though, so if we use all of our values, we should have 2. And so our K sub P value is 1,900. So very similar to calculating the equilibrium constant using concentrations. Okay, so let's look at the relationship between the equilibrium constant and K sub P. So for the general reaction, the relationship between K and K sub P is that K sub P equals K times the gas constant times temperature times this change in N. Delta N represents the sum of the coefficients of the gaseous products minus the sum of the coefficients of the reactants. So if we put that into an expression, it's L plus M coming from L and M up here minus the sum of J and K. Alright, so let's use that relationship. So using the value of K sub P obtained from the previous example, so K sub P is equal to 1900, calculate value of K at 25C. Well, we know that K sub P equals K times RT to the change in N. Okay, well, we know K sub P is 1900. We know R is 0.08206 liter atmospheres over mole Kelvin. We know that T, if it's 25 Celsius plus 273, so that's 298 K. And we know that delta N is the coefficients of the products minus the coefficients of the reactants. So we have one product, so we have 2 minus the sum of 2 plus 1. And so that gives us a negative 1 for our delta N. So what that means is that K sub P equals K times RT to the negative 1. Well, anything to the negative 1 is on the bottom of a fraction. So we can also write this as K over RT. And if I'm solving for K, then that means that K equals K sub P times RT. So let's plug in 1900 times 0.08206 times 298. And I should get 46462.372. Remember, no units. I've still got two significant figures, so 46000. Or you could also write it in scientific notation. Okay, so there are two, let's go back. Alright, so 13.4 talks about two types of equilibria. We've been talking about homogeneous equilibria, which is all reactants and products are in the gas phase, but heterogeneous equilibria is where things are in more than one phase. And the position of the equilibrium does not depend on the amounts of solids or liquids, because the concentration of solids and liquids won't change. And so because they won't change and they don't contribute to the equilibrium, then we don't include them in the equilibrium expression. This would not apply to solutions or gases, just solids and liquids. So let's look at the thermal decomposition of calcium carbonate. Since the calcium carbonate and the calcium oxide are both solids, they aren't included in the equilibrium expression. And so because we do products over reactants, carbon dioxide as a gas is our only product, and it's the only one that's not a solid. So our equilibrium constant is just equal to the concentration of CO2. Okay, let's look at the decomposition of liquid water. Okay, well here the water is a liquid, so it is not included, and so our equilibrium expression is just H2 squared times concentration of O2. Since oxygen and hydrogen are also gases, we can also write the case of p-value using the same idea as we used for the equilibrium constant. Only now we're using partial pressures, or pressure at equilibrium. Okay, let's look at the decomposition of gaseous water. Now that all the reactants and products are gases, we can include H2O. And so we've got, here's our equilibrium expression, and here's the one in terms of pressure. Okay, let's look at an example for K in case of P. I want to write the expressions for K in case of P for the following processes. Okay, we have solid phosphorus pentachloride. So phosphorus penta means 5, so PCl5, it's a solid. Decomposes to liquid phosphorus trichloride, so PCl3, and chlorine gas. Okay, well we know that the only things that can be included in the equilibrium expression are gases and solutions. So PCl3 is out and PCl5 is out. So K is just equal. Oh, before we do that, we need to balance. So let's see, we've got 3 and 2, 5. Okay, we're good. Everything's 1 to 1. So this is concentration of just Cl2. And because it's a gas, we can also write K sub P equal to the equilibrium pressure of Cl2. Okay, let's look at another one. We've got deep blue solid copper 2 sulfate pentahydrate. So Cu, that means it's a +2. Sulfate's a -2. Pentahydrate means there's 5 H2Os. And it's heated to drive off water vapor to form white solid copper 2 sulfate. So we've got CuSO4, that's a solid, and we're driving off water vapor, so H2O as a gas. And it said this was a solid. Okay, we need to balance real quick, so I need 5 waters. Everything else looks good. This is a solid, it won't be included. Copper 2 sulfate is a solid, it won't be included. We're just left with the gaseous water. So K is equal to the concentration of H2O to the 5th power because of the 5. And if I wanted to write K sub P, that's equal to the partial pressure of H2O to the 5th. Okay, so here are the homework. We'll work on these in class. Have a good day.